Okay, so a new unit, understanding the gas laws. Okay, so let's get into a little bit of background here. Let's talk about where these gas laws came from before we move on too much farther. Um, so we're talking about gas laws. The main thing we're going to be looking at is pressure. And something we know is we need to know the units of pressure. So the one we tend to use the most in chemistry is atmospheres. 1 atmosphere is the amount of pressure that's in the air at sea level. And as you go up, if you notice your ears ever get a little bit lighter and start to hurt, it's because the pressure is changing. If you go to the bottom of your pool, the pressure is changing. And that's changing how your eardrums are affected by those different pressures. So pressure is important to us in reactions. Now there are different units of pressure. For example, 1 atmosphere is equal to 760 torr. It's also equal to 760 millimeters of mercury, mmHgs. You have some other units of pressure. 1 atmosphere also equals 101.3 kilopascals. And the American unit is 14.2 psi, which is pounds per square inch. Most of you are familiar maybe with the bottom ones. Torr is a little weird, and especially because it equals mmHg. Torr is a unit of pressure named after Evangelista Torricelli. Torricelli was the person who invented the first barometer and actually figured out that our air around us is an example of pressure. He did it in a unique way. It's a good story, and you'll get that in class. But these are our different units of pressure. Now at this time, we tried to figure out, well, what's going on with the pressure. And what we looked at is we cared about pressure, and we saw that there was some involvement of volume. In all cases, volumes were measured in meters cubed or a liter. Okay, it's basically how we tended to check things out. In class, you'll see it as centimeters cubed a lot, which is equal to a milliliter. It's because we do a lot of work with that. And so we have pressure and volume, and we knew they were related. The other aspect that we started to see that, wait a minute, when I change these things, I have temperature differences. And temperatures is going to be originally in degrees Celsius, but we also are going to measure it in Kelvin. K is for Kelvin. And every once in a while, degrees Fahrenheit. But for science, we like these scales a lot better for what we're working with. And so we're going to work with that temperature. And so now we had some individuals. Essentially in the 18th century is when this became very popular study. And the work was done to understand the relationship between pressure, volume, and temperature. And so the first scientist came around that did work on this was Boyle. And Boyle's law states, just one law that we're working on, that initial pressure is going to equal to some other pressure times volume. And so what we're saying here, if I increase pressure, what will happen is volume will decrease. That's what this one. So pressure and volume are inversely related is what Boyle's law states. Then you have Charles' law. And Charles' law basically said that, you know what, if I look at volume, volume is directly proportionate to temperature. So if I increase temperature, volume will increase if pressure is held constant. In Boyle's law, it's assumed that temperature is constant. That's why it's not there. And then we have one more, and that's Gay-Lussac's law. Gay-Lussac actually came up with 2 laws. The one more important right now is that pressure and temperature are directly related. And he also brought in the fact that it's the number of moles. The amount of material does affect these things, is Gay-Lussac's law. We'll get to that more in a minute. Now, all of these laws were individual laws until we put them together to get the combined gas law. The combined gas law simply says that if you have an initial state of pressure, volume, and temperature, this will equal a new state of pressure, volume, and temperature. This was our combined gas laws. You notice I took all of these gas laws and I put them together to get this. This will be a very important formula for us in the future. We're going to work with it, we're going to see what it means and how we can calculate changes in material based upon changes of pressure, volume, and temperature. With that, I'll see you in the future.